Every year, eminent metallurgists in the country are invited to deliver this talk. This year, we are fortunate to have with us Dr. Madangopal Krishnan, Director, Materials Group at Bhabha Atomic Research Center, who will deliver the Professor V Sundaram Memorial Lecture. Dr. Madangopal Krishnan had done his Bachelor's of Technology, Metallurgical Engineering from Institute of Technology, Banaras Hindu University in 1983. This was the time, early 80s, when Banaras, BHU, for metallurgists was known to be the Makkah of metallurgy in the country. The topmost, the group which was active there at that time, later on dispersed throughout the country and contributed significantly through different organizations and universities in the field of metallurgy and materials. And from this premier institute in metallurgy came Dr. Madangopal Krishnan. He came in 1984 to Bhabha Atomic Research Center, joined the 28th batch of DRC training school, and graduated from there in 1985 and joined Bhabha Atomic Research Center. Dr. Banerjee, I remember, played a major role in Dr. Madan Gopal joining this particular group, the TM group, which was there in physical metallurgy that time in DRC. Here, Dr. Madan Gopal started working right from day one, I believe. He was working on martensitic transformation, phase transformation, especially the martensitic transformations, and its application towards shape memorials. This has been a very significant contribution of Dr. Madan Gopal, because not only fully developing the understanding, mechanistic understanding of these transformations, martensitic transformations and shape memory effect in materials, Dr. Madan Gopal took it to the application stage. The couplings which are currently being used in our indigenous fighter planes, this technology was developed by him and his group, and later on it was transferred to Ministry of Defense and a plant was set up at Bangalore, full-fledged plant to produce these couplings in required quantities with the help of Dr. Madan Gopal. Dr. Madan Gopal had, like I said, that electron microscopy, phase transmission, processing of materials has been his initial passion, but over last 1 decade, he has also been steering the group which is working on ceramics and glasses and its applications in optical, biomedical, and nuclear applications in the department. Dr. Madan Gopal obviously has been bestowed with several awards. To begin with, the Bhabha Award of the Trading School in 1985, Outstanding Researcher Investigation Award, DAE SRC, prestigious award in 2005, the highest award in Department of Atomic Energy, Homi Bhabha Science and Technology Award in 2007, Best Metallurgist of the Year Award by Ministry of Steel through IIM, he got in 2008, and several other awards, including Indian Society for Advancement of Materials and Processing Engineering in 2010, Path-Breaking Researcher and Outstanding Technology Development Award of DRDO in 2012 from Ministry of Defense, and the Vasvik Industrial Research Award in 2015. BHU also recognized him as Distinguished Alumnus recently, and he has been a JSPS Fellow earlier. Currently, Dr. Madan Gopal is a Distinguished Scientist in the Department of Atomic Energy and Director of the Materials Group at Bhabha Atomic Research Center. I invite Dr. Madan Gopal Krishnan to deliver the Professor V Sundaram Memorial Lecture.
So in the beginning, I must thank all the organizers of the Mumbai chapter for having invited me to present this talk on shape memory alloys. for the V Sundaram Memorial Lecture. And also, I must thank all the people who joined in to listen today on this talk. I think that's a very important thing to join in and show support for this. We do have some technical difficulties now and then, but I thank you all for showing that support. This is an annual event and it is a very important thing for the chapter. I see Dr. Banerjee also there, and Dr. Banerjee will, I mean, it goes back to his memories when he was as one of the prime, I mean, reason why this IIM chapter also has seen that strength. Because I think for some time before that, it was also not doing too well. And then with this initiative and Professor Sundaram's initiative, it has started again. And I see also Mr. PK Shah, sort of all the very old members of IIM who are here. I thank them for having come for this lecture and to show the support. So I'll start my talk, and this is a little dated in that sense that shape memory alloys have been around for quite some time, and also that some of the information that I'm giving here today is a little, I have not sort of updated in one sense, but I believe that it is still a material which is very fascinating, and I still am in awe when I see it functioning in your life. So I hope you too will share that kind of enthusiasm when you see that in action. And some of the slides, I hopefully it works. Otherwise, I'll make up for it talking. So I will move on to my first slide. And I hope everything works. Okay, so in the shape memory effect, so basically it is shown by a class of materials, and this effect in sense that after you deform it and you heat it, that is one kind of trigger that you can give, and it will come back to its original shape and dimensions. Of course, when you look at polymers use and or also disorder, I mean some of this kind of materials like polymers or glass ceramics, you can think of other kind of triggers. In polymers, particularly, you can think of pH or you put ultraviolet light and things like that. So you have to trigger the event, and you give the deformation, and it comes back to its original shape and dimensions. So we will talk essentially of metallic materials, and that to the work which we have done here primarily, that's on nickel titanium shape memory alloy. So by and large, the talk will be on that, and there's the largest class of materials. So to show you what it really looks like, I have to now this one. It was working here sometime back. Yeah. So what you can see here is a flower, and I think I see Dr. Banerjee, so I keep referring to Dr. Banerjee all the time. So it is Dr. Banerjee's idea to make a flower, and this goes back sometime when I think it was Rajiv Gandhi who was coming here for a meet, and it was suggested that we put something to show or showcase some of the things that we have made. And I was fresh out of training school at that time. So one of the ideas they had is a simple thing that appeals to all was to make a shape memory flower. And so what this is that you have taken nickel titanium, arc melted it. This one is equiatomic, which means 50-50 atom percent. So roughly the weight percent will be 45-55. And you hot roll it, and this has been additionally chemically polished, so that's why it's so bright. And some petals have been cut out, it has been stacked into a flower, and it's very soft at room temperature. So when you deform it, you can very easily do so. It's about 100 MPa is the stress that you require to deform it. And when you put into hot water, so this temperature water is something like about 80 degrees. And when you put it into hot water, it recovers. So you see that whatever you do to it, you can, I mean, this of course is in loop, this video, but of course, if the flower is around, you can see that you can still do to it. You can keep deforming it, and it's amazing. It's just, it keeps springing back to its original dimensions. So if I'm to look at it from a material point of view, I point out, I mean, I take your attention to the figure on the right-hand side. So what you see here is that there is it's like a stress strain diagram. So, you deform the material in a room temperature, and when you undo it, it remains, I mean, sort of unload it, it remains more or less where it is. So that's the set or the plastic deformation that you give to it. But if you heat it, so somewhere at a temperature above, which we'll refer to as AS, it starts recovering its original dimensions, and by about AF, it has completed that recovery of dimensions. So, and you cool it somewhere at a temperature MS, it starts softening, or it starts acquiring this property of becoming soft. and then by about MF, it is back into its very soft and pliable state where you can deform it again, and you can cycle this whole thing, and when you heat it, it once again recovers. So this state when it is at room temperature, as is shown in this case, is its martensitic condition. And when we heat it, we'll refer to this as the austenitic condition, where it has recovered its original shape. And as it happens that at room temperature, it's in one crystal structure, and when you heat it, it is this reverse martensite to austenite transformation that restores its original shape. So you have a phase transformation that is responsible for restoring its original shape. So in the martensitic condition, unlike what we are experiencing in other kind of alloys, we see that it is very soft and it's pliable. So there are mechanisms of deformation which we can quite understand that it won't be the conventional plastic deformation where you have shear with some dissipative aided by dislocation. So that's a kind of a dissipative process. So that would not be the basis of such a kind of macroscopic shape change. So I will use this word very often, macroscopic shape change. So you're only seeing the shape change. So microscopically, it is not the plastic deformation that we are very familiar with. So it will change the shape and you're able to deform it. And when you heat it, it recovers its original dimensions. Now, there is something that's interesting that happens when you deform it in the austenitic condition. I'll show it in the next slide. So in the austenitic condition, when you deform it, you have this thing called stress-induced martensite, where when you apply stress, the phase which was stable at room temperature, we have just told that martensite with a soft and pliable state is at the room temperature. That you can stress-induce. And it shows a very large strain that way. And after a certain extent, let's say 6%, beyond which you can't strain it, again, the load you'll see will go up. So at this point, if you unload it, you will get back the original dimensions. So here it is that this animation shows you that there is a single crystal of austenite, and when you deform it, you have the martensite crystal, nucleating and growing, and the plateau corresponds to the constant stress at which the martensite will more or less grow to its maximum, and that will be when the whole sample is consumed. And this will show a maximum strain of about 6% or 10%. That is about, in these alloys and nickel titanium, you expect to see that. And that is the same as what you will get if you had started with that soft and pliable condition. And when you unload it, it will go back to its original shape again, because this martensite is not stable at this load, and you have stress induced after all, and it will return back. And much like you had seen this AS and AF, the temperatures at which, or the MS and AS, the temperatures at which you get martensite and austenite, you'll have an analogous stress here, as the initial stress at this martensite will form is sigma MS, and at the stress at which it will start returning is sigma AS. So you can see this behavior is analogous to what happens here when you're cooling. So you're having a transformation in thermal under a force. I mean, in the sense that you're giving a supercooling when you're cooling it. So you have a supercooling and superheating, much the same way you have a super heating and supercooling in an analogous fashion when you stress it and unload it. So that is about this behavior, and this is referred to as superelastic. And this one, which you have seen in the deformation which has happened in the martensitic condition, is called pseudoplastic. And pseudoplastic, why? Because you're recovering it. So you have this also is referred that way to pseudoelastic, but I'll be calling it by superelastic, what is commercially it is applied, the way it is, where the applications are called. So these are superelastic nickel titanium alloys, and what is preferred is if you have it austenitic at room temperature, when you can actually deform it and recover it. And if you had martensitic at room temperature, you would of course have an application at a much higher temperature where you heat it and recover it. So we'll see in the next slide one application of superelastic, which is the superelastic stents. Now, this is the most, I would say, outstanding example of superelasticity. And in this, the nickel titanium superelastic alloys, which is actually a material which has got the, or nickel titanium alloy, which has got the austenite stable at room temperature. Now, which means to say that I can change this temperature. So that's what comes when with alloying, that you can alloy nickel titanium with ternary additions and change this transformation temperature. We'll talk about it in a couple of slides later. So what is done is that you make another alloy of nickel titanium, say nickel titanium copper or chromium, and bring the transformation temperature such that it's austenite at room temperature. And now it is superelastic. So a tube of such a kind of nickel titanium, what they do is laser cut it, and it can show it's about as thin as about 25 to 50 microns. So it's very pliable. It's almost indestructible at this thicknesses, and also that they make it like a drill, so it can accommodate all the deformation. And when you put it into a cannula or a catheter or something like that, you can push it in, take it to the location where you need to deploy it, and as it comes out, it'll unfurl to its original shape. So that is the property of superelastic strengths. And by and large, if you look in the market, as far as peripheral strengths are concerned, more or less it's all superelastic strengths that are dominating. And if it is vascular strengths, that's from vascular circuit, you will find that maybe about 50% are superelastic strengths. It's amazing and magical material. I'll show you another application just to buttress this point about superelastic. And there are several such applications you will see, but one that I found and very cute and can be as an example is this on spectacles. Of course, it must be very expensive. I never tried to buy one myself, but you can see that it is for people who are accident prone. And at least I know one, that is myself. You put your specs on your seat and occasionally sit on it, and that you regret. So this is something that can, in a way, for those people and for many others, it stands out as a wonderful application. But one can conceive of other superelastic one using, clothing and certain bracelets and things like that, where you totally unfurl and it comes back to the original shape. It's basically playing on the same theme that it is superelastic. I'll show you a few more examples a little later. But what I will do now is to give a picture of all the shape memory alloys, which are sort of, it's only a small list of them, but these are the most outstanding shape memory alloys which either been put to in some application or very potentially close to some application. Of course, I mentioned the nickel titanium shape memory alloy, and as given here, there are a lot of ternary additions, and a reason I've already mentioned is that you try to reduce the transformation temperature. Of course, one can also try to increase the transformation temperature. They have been of interest, like zirconium and hafnium is added for that purpose. But some of these alloying elements which are added to nickel titanium is because nickel titanium ion is by and large the simplest of shape memory alloys which are for engineering applications. But there are some prejudices. So because of it, for applications in the human body, so they add copper or chromium, and such kind of things are there of alloying elements. And more or less the theme is the same, that you add the alloying element. Now this element, either, if you see, nickel titanium is an ordered intermetallic, and this will be seen in a picture later when I show it. So it's like a beetle CSCL structure, as they call it, and the nickel and titanium occupy their own respective positions. So when you add iron or copper or aluminum, this is done either it substitutes for nickel or it substitutes for titanium. I think I'll discuss it a little later when the slide comes. And such is the case with copper, also copper-based alloys. This is also an ordered intermetallic, and so is nickel, manganese, gallium. But iron-based and titanium-based alloys are disordered. So this class is called the thermoelastic, which is all ordered. And somehow the ordering is important for the shape memory too, because order makes the material a little more stiffer, difficult to deform, and all that goes into memory. I think if I get a chance to speak on it maybe later in some slide, I'll tell that why that can be of some kind of help as far as the reversibility is concerned. And this of course is iron, manganese, silicon, nickel, chromium will be based on the stainless steel alloys, and it's very close to the chromium or 9 chromium and above, or stainless steels. So of course, the stainless steel shape memory is an ideal shape memory, but you can see that basically the purpose of this is to get a epsilon martensite and to prevent the alpha martensite coming out under stress. So that is the design of these alloys. It's a alloy basically. It is something that is very cheap and very easy to make, but the difficulty would be in that it's got a very small amount of strain, and so far it has got, I think, a couple of applications have been done. It is still waiting for the big time deployment. And of course, titanium shape memory alloys, one can imagine, is biocompatible, so it'll have some application in the human body. But more than that, it is biomechanically compatible. And if you start with something like porous titanium-based alloys, the biomechanical compatibility comes because the modulus is close to that of bone. So something with its porous titanium-based alloys will have a modulus very close to about 10, 12 GPa, which is very quite good and close to bone. So that makes sense because you don't want something to loosen. Otherwise, there is some stress localization that happens if you make components, and it should be seamless. For that reason, titanium alloys I look forward to. NIM and GA, I just made a mention here. There's a class of ferromagnetic shape memory alloys, a very large class of alloys, and a lot of work has gone on in this direction. And the attraction is that in addition to having the usual shape memory, you also have, you can have the parent phase as a magnetic phase, or a ferromagnetic phase, or you can have the martensite as a ferromagnetic phase, or you can have both of them in which, but the difference could be that one of them has a higher magnetic moment. So what would happen in this case is that you can even have a situation where you stress reduce the parent phase because it is ferromagnetic. So you can use magnetism as or magnetic field as one additional trigger by which you can have memory. Like I mentioned before, you have something like heat, and you can even add stress to that. In addition, you can apply a magnetic field. So these are the classes which I'll just, for the moment, I will only, but in this entire talk, we'll concentrate on nickel titanium shape memory alloys. So just to, I mean, this is the necessary recap, if I'm to put it that way, phase transformation. Since I made a mention of that word, I'll just make a quick, just to put my point of view as what I'm trying to say and not confuse the whole thing about phase transformation. I'm just trying to simplify it the way I look at it. In iron-based alloys, you have starting with austenite FCC and going on to BCC. That is the ferrite. That's the way the transformation takes place. And what you mean by reconstructed transformation is that all these atoms are ripped apart, they diffuse through the lattice, and you reconstruct it at some point at some nucleation site, if it's a heterogeneous site, at some particular choice or site which is preferred over others. So you reconstruct the whole lattice, much like you take the house and tear it down and reconstruct the whole house somewhere else using the same materials. Well, that would be the reconstructed transformation. And I'm going to press it. Okay. And the alternate would be the diffusionless transformation. See, that involved diffusion because you have to diffuse, take all this material and diffuse through the lattice and go to the site where you have to construct it all over again. I mean, of course, a different structure altogether. But if you look at this, what is otherwise called the Bain correspondence here very famously, is that if you take two austenite lattice, close to each other, you can see a cell, which is the BCT, there's a body cell tetragonal cell, which is already very close to the BCC. It's already, the environment is very close. Let me tell you, this is not unique. You have many such environment, but it so happens that this is the closest in terms of its volume, the total change in volume. So this is a very structure that's already very close to the final BCC structure. All you have to do is sort of squash it along the C axis. This is a tetragonal cell. You squash it along the C and stretch this A and B, if I'm to call this A and B. So this is delineated. You've taken it out and you stretch these two and squash it. You come right away to the BCC structure. So without having to break and diffuse the thing, you can still get the original structure. So this is the diffusionless transformation that happens, and a class of this diffusionless transformation is a martensitic transformation. So the martensitic transformation occurs by shear. So what you see here is a shear. And let me see if the next slide I've actually included it. Oh, okay. So I'll just give one point before that, is that the shear itself has several components, and you may have a component which is in which there's only a pure shear, or you can have a component in which you have only the inhomogeneous element that's called shuffle in it. So in this, the martensitic class of transformation is one in which it is dominated by shear. And you could, so if you have the three components of it, usually are dilatation, shear, and shuffle. Now the dilatation means it just is a something like an hydrostatic, either it's an expansion of the lattice by dilatation, or it's a contraction of the lattice, right? Uniformly in all the three axes will suffer the same extent of strain. That's dilatation. And shear would be that you're having a pure shear where one face is shearing in relation to another. And if you have shuffle, it would mean a plane of atoms are shuffling like cards. Like if it's for this case, it would be this plane shuffling with respect to each other, where the center of gravity has not changed, and the purpose of this would be slightly moving this atom to another location of choice. Now, it so happens in the general case, all the three are required to move the atom to the final position in any phase transformation, which is diffusionless. But you could have instances where you have only dilatation, or you have only shear, or you have only shuffle. All three nature plays with this, and everything is possible. But martensite is different from all of them in the sense that it is dominated by a shear. So it's essentially a shear transformation. The dilatation here is less than 1%. And you have a little bit of shuffle. So I'll show that in this case in nickel titanium alloys, you start with the B2 structure. And to get to this, again, you have to take, this is having 2 atoms per unit cell, and this has got 4. So you take 4 such cells and delineate this, what is a tetragonal cell out of that. And in order to get to this monoclinic, you have to change these 3 axes likewise to the 3 orthorhombic axes. So this is the orthorhombic cell that you get. And then you shear this plane with respect to this, if I call this O1 plane, these 2 planes, we shear with respect to each other. So this angle becomes something like 96.8. And the final act which you have to do is that you see these 4 atoms that are here, these 2, I think if I call it red and 2 green atoms, you have to just shuffle this face with these 3 faces. So you have 3 faces, which is the O1O plane. You just shuffle with respect to each other. And you can see this green has come in, and there's one green which is exited. That was here, exited the space. So what is happening is that this was the base-centered monoclinic, and now it has, from the base center, it has moved away slightly, and it becomes a primitive monoclinic. So what you have done essentially is started with a primitive cubic and transformed to a primitive monoclinic, and with a very small amount of shear and shuffle. So to explain this now, to get out of this very deep explanation and to look at it in a very simple way, is this animation helps us there. And you can see you start with the cubic, and this is the delineated cell which has been stacked up. You can see it's quite faithful. If you look at this kind of animation, you can see that there is a shuffle here that's happening. But what the picture that you should take away from this is that you're having a shear and there's a change of shape. Now, it is a change of shape that we are looking forward. So any shear which gives rise to change of shape. The plastic deformation is also a shear, and that also is required by a change of shape. So here I can deliver a change of shape with this shear. Okay, I move on to the next slide. One thing more I have to mention before I show you the microstructure is I'll use this word orientation variance, and therefore I brought in this slide. So if you start with only a tetragonal transformation, that means I'm going to essentially only stretch the C axis. So we take this basis, and let's say this is the original basis to which we'll refer all this transformation. We start with this cube, and if we stretch it along the Z, we get this variant. If we stretch it along the X, we get this orientation. And if we stretch it along the Y, in a relative term, we get this variant. So you have 3 orientational variants which are sort of with respect to each other, they have got different orientations. Now, in the normal case, if you take the martensite, where we have taken a very specific case of having a tetragonal transformation, but if you have in a very specific, general case, we have about 24 orientation variants that result. Now, so if you look at the martensite microstructure of copper zinc aluminium, this is a 691417 alloy which has got a martensite at room temperature called an 18R monoclinic martensite. And if you look at this vertical alloy, you will see that there are 24 orientational variants. And the way to see it is, if you see these 4 of them, you see, I have to fight with this mouse also. So you see 1, 2, 3, 4. It's something like a wedge. So this is called the diamond morphology, and this is like several chevrons piled into each other. And this kind of diamond morphology has got this one of the particular groups of 4 variants which are together. So 6 such groups come together and give you the 24 orientation variants. So the thing to take away from this, one thing I need to mention before that, there's an optical microscopy and an optical micrograph, and the contrast has been given by using polarizing filters. So that's the way you're able to see this different variants, because this is a monoclinic martensite, so it is, it's active under polarized light, and you're able to see these variants. Okay, to come back to this, the one thing that stands out in this microstructure is that this kind of feature where these martensite variants come together, and that's because of this is referred to as self-accommodation, and that's because of the fact that each of this martensite variant in isolation has a shear, and when put all together in a group, their shears cancel each other. The purpose of this is that if an isolated group is sort of nucleates in a, let's say you're telling it 0 time, it nucleates in the austenite grain, then what would happen is there would be a stress field around it, and that acts against the nucleation. It turns out that the kind of free energy available for the nucleation is not very high. So, and you can just imagine, it's very close to room temperature also. We have already seen a transformation which is 80 degrees. We have seen that. These are all very low temperature, and the driving force is not high. And the only way it overcomes that, and if you have a stress around the plate, that will act against that. That will dissuade this formation of the martensite. And the way it gets around this is by forming a self-accommodating plate group. So essentially, the parent phase around it does not see much because all of this cancel each other. So this self-accommodating martensitic microstructure is characteristic of the shape memory alloy. In addition, there's something I'll make a mention, but there are no supporting things which I can see here, is that these interfaces are very typical, and we'll mention it again in the following the slides to come, is that these interfaces are also glissile. They're very easy to move around. And it so turns out they're also twin interfaces. Most of them are twin interfaces, and they're very easy to move around. So unlike other martensitic microstructures, this is entirely different in the case of shape memory. So if I take the next slide, I will show here what we see is a nickel titanium shape memory alloy, which we will show the examples entirely in this talk will be from this alloy. And what's different here is that, to start with, you can see these three plates coming together. So I made a mention in that other case. Okay, I forgot something I should have told earlier on, that this is a transmission electron micrograph, and the contrast you see here is what is called diffraction contrast. Is essentially because the crystals are slightly oriented or oriented different with respect to each other. Certain things are very close to scattering because they're closer to the Bragg condition. They scatter more, and some scatter less. And so that contrast which you get, the dark and light, is that one that scatters more appear darker, and the one that scatters less appear brighter because everything comes in through the aperture. And you can see this dark and light contrast, and that's what you're seeing. But it helps us to see this because you can see that there are two different orientations within this. So this is an interesting feature of martensite also. The martensite that forms, it forms what is called an invariant plane strain. Now I won't go into that, but what it has to fulfill a condition called invariant plane strain, and generally that shear which we talked about earlier is not able to do that. So it is just not the shear. It has to maintain this invariant plane strain, and in order to do that, it needs to have one more shear, and that shear in this case of in nickel titanium and other shape memory martensite could be twinning. So you don't have slip. Slip is also possible that you don't see. So in many of these martensites, you see this kind of internal feature which is called internal twinning, a lattice invariant shear, which in this case is twinning. And you see martensites without this feature because those are cases where you don't require the shear in order to meet that condition which I said is invariant plane strain. So you see this substructure within this martensite. All in all, you see three variants getting together, and you can see this substructure helps you to identify the orientation of the plate, and these three plates come together and give you a three variant cluster. And so that's the case of the B19 martensite. And if I take nickel titanium copper, it's interesting because it is an orthorhombic martensite, so that monoclinic, that 96.8 is now 90 degrees, and it's an orthorhombic structure. And these three plates which come together, one thing more interesting is that you don't have any substructure in this, because it doesn't require the lattice invariant shear in order to be an IPS. Such is the case, and so this is a very ideal case where it's straight away it's in getting plane strain, and you don't see any substructure, but you can nevertheless see these three plates, and they form a triangular morphology. What's more interesting about this is that it has got actually 6 plates. To see that, you have these 3 plates on stacked on another 3 variants which are stacked together, and they're like, you put some straw hats, you stack them all together, how it will appear. And it becomes more clear when you section them along a vertex. You can see chevrons along the thing. So you see this chevron structure along one side. So this is a very interesting arrangement where you got 6 variants coming together and having a very common axis. This is the one common axis that you have. And what they try to do effectively is to give rise to self-accommodation, that is minimizing this strain felt by the parent phase. So that is a self-accommodation. So I wanted to conclude this part of the microstructure by saying this is very typical of the martensite, they say. And the other thing is that it's a little different from the martensites of alloys which do not show shape memory, and this is a very key feature of it. So going beyond this, I will just try to in as short as possible. I'll try to explain what the shape memory effect could really be due to. So you start with an austenite, let us say crystal, and when you cool it, you get a polyvariant martensite microstructure. What this polyvariant means, you got a lot of orientation variant. We said up to 24, and you've seen an example in the case of copper, zinc, aluminum, and nickel titanium. You got a lot of variants of microstructure which form the self-accommodating martensite. And what you've done is pseudoplastic deformation. We've done a deformation which is very different from conventional deformation, and you've got a macroscopic shape change. A shape change, as you've seen in the case of flower, it was crushed into a bud. But when we heat it, there's a microstructural reversibility wherein all these grains of all this orientation of martensite, they all coalesce and give this original grain of the austenite. So one can ask this question that if there are 24 variants when you cool it, there could be a few crystals as they go back. It needn't be just one. And so that's the important thing, that you also have a choice of orientation of the austenite grain when you heat it. And what this microstructural reversibility assures you is that that will not happen, and all of them will give rise to the original one that is started. And if you're seeing that flower, if you remember that, if the flower was, I said, hot rolled, and it was made into flat strips. So that was its shape in which the austenite was made. And all we did is we cut the flowers, and when we deform it, that is what we have done here in this case of pseudoplastic deformation. And when you cool it, you'll get the polyvariant martensitic microstructure, and when you deform it, you'll get the pseudoplastic deformation. Something happens, and you have this macroscopic shape change. But when we heat it, we get back to the austenite or how it was shaped in that hot condition, or thereafter, if you have machined it into some shape, whatever it was in that condition, you'll get back to that. So here, the two important parts of this shape memory is one is pseudoplastic deformation, and the other is microstructural reversibility. So these are two parts to it that give rise to the entire shape memory effect. It has to show you a deformation which does not matter. It can be sort of undone. And then when you do microstructural reversibility, it gets back to its original form. In that sense, it is not memory as it doesn't remember that way. Whatever you've done to it, it will sort of undo it. So you could do just about anything and it'll undo it. And so therefore this, we will look again in the next, I hope this slide cooperates with me. Let's hope. And we have these two things, and with a couple of animations, we'll try to explain what the pseudoplastic deformation is. In this case, we are considering two variants of martensite, two orientation variants, I'll use that word. So one which is a colored yellow and that a colored orange, and I'll just take for the purpose of this slide that yellow is favored by tension. Now it's a shear. So something, tension favors one orientation and compression would favor the other. So this has been, in this case, tension will favor the yellow and compression will favor the orange. And I made a mention of the fact that the interface between this martensite is very glissile, which means to say it can move. And how would it move? If it moves, then let me click on it and then you can see. And nothing happened. Okay. Okay, something happened. Okay, now you can see that the yellow one is consuming the orange one, or rather the extension is happening because the yellow one is consuming the orange variant, which is not favored under compression. So this way it shows an elongation, and if I would do the same thing in compression, it would be the orange one that would go at the expense of the yellow, and then one can guess what will happen during bending. All in all, it says that pseudoplastic deformation, you can get a macroscopic shape change essentially by rearrangement of the variants, and it happens so because you are able to move these variants. And this, what has happened in the movement of this glissile interface is that you're twinning. Basically, you're twinning. So there's a twinning transformation, if you want to call it that way. There's a twinning transformation that happens when the glissile interface moves, and in this way, it rearranges the entire microstructure, and you see a macroscopic change. And if you start with the 24 variants, then they will cancel the shape strain, and you'll get essentially the same shape that you started off before you cooled it. But when you do this deformation, you're getting a macroscopic shape change because you've got some variant which in fraction is some volume fraction is more than the other. So its shape strain will express itself, and then that is seen as a shape strain or a macroscopic shape change. And when you heat it, however, if it were an irreversible material like you would see any normal steel, and I will try again. Yeah, if it's an irreversible material, then this is just an animation to sort of rub in the point. So you start with a austenite structure, and then when you cool it, you get martensite. When you get back, you get various orientations of the. Maybe I need to see this again. You will see various orientation of the grains because there is a reversibility. You can see the several orientations of the austenite that is there, And in the case of reversible microstructure, it'll get back to its original. So you have two situations here. One is pseudoplastic deformation, which you have a deformation which only sort of, it doesn't have any dissipative mechanism. And you can just change the shape and nothing much happens in terms of if you have an energy landscape. All you've done is you expended the energy in a sense that friction. You move the interface and you lose something in heat. Nothing much else has happened. But in the microstructure reversibility, whatever you have done and whichever way it's arranged, it gets back to the original crystal. So these two things are phenomena behind the shape memory. So these animations, I hope, have conveyed that point. So I will just start with this slide again, just to show you some of the evidence of this microstructural reversibility, because we made this claim that you can somehow, with a polyvariant microstructure like this, get back to this situation where everything will coalesce and give rise to the original grain, despite the fact that it can give rise to different orientations. The challenge is this, that when you get a microstructure like this, you get austenite nucleating at different points. Now, in the case of monoclinic, I can tell you that each of these crystals can give rise to two orientations. Now, so all these orientations which nucleate at different points of the microstructure during the reverse transformation should give rise to the original orientation of austenite. Otherwise, you'll get irreversibility, or you'll get a grain refinement, as you see in steel more popularly. So how does it do it? So there has to be some kind of a restriction on the way this interfaces, that it should give rise to, even across space, that the orientation remains the same. And it can do that one way, and to discuss it, I will bring along some which I have otherwise also referred to as a mumbo jumbo, but I will bring along this, which it's actually a very good reduction in the discussion. So it's for it. All I want to say with this is that you start with a parent phase and you come down to a monoclinic in just on the basis of symmetry. If it's a language of symmetry. If you see that, and it says you get 24 variants. Now this is what we started off with. If we don't have any special relationship between these two variants, and we don't sort of have any intersecting feature, any special symmetry axis or something which will sort of reduce the symmetry, you'll give 24 variants. And if on the way back, when you start with a monoclinic and you go back to the parent phase, you see you will get two variants, because you have not had any restriction whatsoever. But if you have a restriction of a kind which I'll mention here, is that I will just give in a nutshell the final story, that if the interface is a twin interface, that means the twin in the monoclinic structure, but derived from a mirror plane of the parent phase, then in that case, you will get a single variant. So that is the kind of restriction we can imagine, that if we have a kind of a restriction as much as something like that, we can get the single crystal. So I'll just hop beyond this slide and take three conditions under which it will happen. This is among the last of those which I will show. So I'll not take much more time on this kind of a discussion, which appears to be deep. I just wanted to say that all it means is that there's some restrictions. So I refer back to the original nickel titanium microstructure which you've seen. I've said that there is a substructure which is internally twin. Now just imagine, that's the most difficult case. If you have two nickel titanium orientational variants coming next to each other, the ideal and the best condition is that whatever we have spoken earlier on, that this condition that you have to have a twin interface right away comes. It's a great coincidence that it comes right away, and one single interface twin relates both of them. Now that's the best, and that's among the wish list what we want. So it does happen so that in some of the variants it can be the case that you have such a situation where a single interface can twin relate both the major and minor twin fraction. But in case the minor twin fraction is not twin related, now that is a disturbing element. Why should it ever you get this situation? So let's take a case where the minor fellow is not twin related. Then it still can form a twin interface if we pinch it away. Essentially, by pinching it away, what it means is that at the interface there is no minor twin fraction. It is only the major exists at this very point. So at that point, you will have only the major twin related, and it's so easy to twin relate, because that we have started out saying that it is twin related. And in the case where both are not twin related, now that's the worst case scenario, then you have to conceive of a situation where there is another fellow who will come in between, called the bridge variant, and that will twin relate these two. And with that, I will go to the next slide and say this can be taken as a theoretical exercise, and we can see that it turns out that out of the 276 possible combinations, there are only 13 of them in the case of nickel titanium, and it so happens that 4 of them are the best condition that we have talked about. 4 of them you can pinch away, and 4 of them form this bridge variant, and there is one which is called boundaryless, and I'm not going to show you probably an example of that boundaryless. I'll skip this, but I'll say that you can have a bridge. And so I'll say that in this exercise, which is basically a thought, let's say, exercise so far, and I will show you an evidence that there are such kind of restrictions, we can say somehow we can get a kind of a restriction at the interface or some crystallographic restriction and ensure that there is reversibility. And here I present the first case where there's a single interface, a situation in which both the major and minor twin fraction are twin related. And you can see this, it looks very much like the figure which is shown before, very ideal case where both are twin related. And there are only 4 such out of the 13 unique combinations. And the general case I said is, or a more general case would be one in which the minor twin fraction is not twin related. And here is the evidence. And you see that the minor twin fraction tapering away. And when they taper away, you're getting just a single interface where the major twin fraction is twin related. So this is the situation, and this is evidence. If I turn it around and say that this is the evidence that there is something happening at the microstructural level in order to obey this condition, that there is what we call a twin interface, which is derived from mirror plane of the parent place. And if I go across, here, if I go across, I'll show you the bridge combination. This I told was the most undesirable but necessary situation where both of them are not twin related, and you have this O1 twin, as they call it, as forming, it stitches it something like that, like a zipper. It stitches both the variants together, and this also forms a twin interface which can revert back to the original grain. All in all, I will just summarize this and say we started off with a contention that we have to have crystallographic sort of restrictions or some kind of restrictions imposed so that we can get the original variant back. The nickel titanium gives us the best examples of that, where there are these features which we have sort of in the way guessed out that what may be the case. We see several evidence of this happening within the microstructure, that these microstructural restrictions give rise to the reversibility of the. And only additional point I will say is that if there were no restrictions and there were irreversibility, you wouldn't have had the transformation, the reverse transformation happening at 80 degrees. It's very difficult to think that you can have the parent phase coming out at 80 degrees. You have to have a much higher driving force, and you have to go to much higher temperatures to get the austenite or the several orientations, because they're forming fresh grains. So you have to go to higher temperatures, and consequently those alloys which show martensite, which are irreversible, have a larger hysteresis. Here this hysteresis is small. That's one more characteristic of the shape memory alloy. The hysteresis is small. So all of these things come together: the glacial interface, the reason why it is ordered, the twins that you see in the martensite, and the fact that they have some kind of crystallographic restrictions. And I'm trying to move. Okay. Now at this point, I will peel away from all this, and I will go on to some applications. I start with that what we have discussed earlier, that super elastic applications. So this was a stent which we have I had shown earlier, but you can imagine this would be, in terms of the volume of application, the number of applications, perhaps biomedical applications would dominate in shape memory. And that's, as far as nickel titanium, that is true, because nickel titanium is biocompatible also. So because of the titanium alloy, the titanium and forming titania layer on the top, so it's biocompatible. Though there are some who feel that nickel can cause some issues, but by and large, it is the titania protects the nickel titanium, and you find a lot of applications in the human body. And superelastic, one can think, if you want steerable instruments and you want to sort of take it through those difficult areas of the human body, you can have such kind of instruments, and or grasp something which you want to retrieve from the body. And also there is something called the atrial defect, where the kids who are born with the septal defects, this is a birth defect where you have the septum of the heart where it has not closed, which it should close at birth. It is not closed, so you have this blood, the bad blood leaking onto the either the ventricular two ventricles, or I think it's called the atrium. something like that. So it's between that, what do you call, it's sort of the bad blood leaks across. So what one has to do is shut it. And the earlier procedure was that you have to have an open heart surgery and stitch it. But this procedure makes it very simple, like what you have done in the case of stent. It's an outpatient procedure. It takes about 10-15 minutes. This is crushed. It has got a polyethylene it's two umbrellas. So it comes from either side and closes the small little, it's on a wall, there is a small hole. So it's pushed through and the umbrella unfurls and shuts it from both sides. So this procedure takes only 10 minutes or 15 minutes. And for a small kid, it makes a lot of difference, these kind of surgeries. So this has been for at least about 20-25 years. This has been deployed, and here in Bombay too. There are a lot of doctors performing this. But by and large, the first application were these arch wires. And these arch wires will sort of bring back teeth which are distant or buck teeth. And what is prior to that is stainless steels were used, and to a great extent stainless steels continue to be used. And what is done in the case of stainless steel is you tighten it, and there is elastic deformation, which is a maximum of 0.5%. So after that relaxes and the teeth has come back a little, then you have to go back to the doctor. And in the US, you have this co-payment to the dentist, which is more expensive than all that you have put in the teeth. So, and you have many visitations to the dentist and you become poorer. So this nickel titanium shape memory alloy is one in which you put and it's got some 6% strain. So when it comes back, the visitations to the dentist is less. So that has been the motivation. So one can think of many applications of this, and these are, so this wires, this starts with nickel titanium wires, and today hollow wires and wires are very easily available. I take you to another example in which I have mentioned before, it's soft at room temperature in the Martensitic condition, and you could also have super elastic at room temperature by if you do some alloying. And of course, this alloying, I did say that you add a ternary alloying element. You can also sort of increase the amount of nickel. So it's nickel added on the titanium side. So that also gives rise to the same effect, pseudoelasticity or superelasticity. In any case, you have a martensitic material. And so what the martensitic material, we made a mention, that's very easy to deform it, and you have all these interfaces shooting across when you deform it. And what it does is that it absorbs the energy. So it sort of converts its frictional loss. So it converts everything into heat. And that's a good thing because you can absorb the energy. And what the superelastic alloy does is it resets it. It sort of brings it back to the original shape. So if you think in terms of a damper, after a seismic event, this is for some dampers where I use in seismic events. So all the energy is absorbed by the martensitic material, and it's reset to fire away once more by the shape memory, the pseudoelastic shape memory. And that has been the basis of I would say, a very large class of applications in Italy. So I would be surprised to see this application already having come out, but there's so many and so many applications of this in Italy. And they have taken this very seriously, and you can see it. And why Italy particularly? Because this has got all historic structures, and they are also most of the country seismically active, and they have lost a lot already by these structures, sort of coming loose. So you can see here, what they've done is again use this, whatever principle I mentioned earlier on, a combination of superelastic and pseudoplastic material, and they have made such kind of devices. And maybe the next slide also shows one such tower in which you have set up these ropes of nickel titanium to absorb the energy. So you have the seismic event go by and the structure is intact. So that is one kind of application. But so far we discussed two, superelastic and also the ones which are free recovery. That means you're deformed it and it comes back to its original shape. Now something else happens if you deform it, constrain it, and don't allow it to get back to its original shape, in which case it would recover it would apply a stress, and that stress is proportional to its urge, its drive to get back to its original shape. It's trying to get back to its original shape, and that stress can be as high as 500 to 1000 MPa. Now that's pretty high. A 500 MPa, 1000 MPa stress, the load that you can generate by just applying a constraint. So the two things in this which I say is, one is that you're recovering its shape. That is, let's say, called stroke. So you take something, deform it, it gets back to, that's the stroke, and this is the load, and this together makes an actuator. So this under constraint would be something like an actuator. And the difference in this actuator is that these are smart actuators. It is sensing temperature and acting. Or like say, if I mentioned earlier, you could also say that some kind of a trigger. So if it is for other materials like polymers and things like that, so a trigger is there, it senses the trigger and actuates. So you have something, again, you're for getting the cycle back to keep cycling, you'll have to have something that again deforms it. So here, before showing you that, let me take you here. Again, it's something that goes down memory lane. And Dr. Banerjee, of course, is also responsible in a way for this. This has been a student project. It goes back to the beginning of my career. And this, what you see here is a single crank multi-piston engine, if you want to put it that way. This single crank is right at the center of this, on which there are several spokes. And on these spokes, there is this white thing that you just see shooting past you is actually what I'll call a piston head. And between the piston head and this wheel, so they're eccentric. I mean, they're sort of a crank where the centers are different. And what you see is that between these two, nickel titanium shape memory loop is actually being deformed. So in the cold water, it is being deformed. In the hot water, it recovers. So you deform it in the cold water, and when you pass it on to the hot water, there's a big stress that develops. And that stress is about 500 MPa. And the stress required to deform is only 100 MPa. And so what you effectively done is converted heat into mechanical energy. So you input this deformation, you input heat, and this is what you get back. So there is quite a good efficiency, and the efficiency is even better if you think that this difference of temperature was 30 degrees. Now this 30 could be minus 80 and minus 50 also, and that's startling. So if you consider that it's minus 50 and minus 80, you can never think of another system that can do this. That's what phase transformation do. And this is not the only example of phase transformation. Phase transformation, giving out heat, giving out energy. I think there are a lot of examples. This is one example where a phase transformation or a phase change system, as they call it nowadays. So that is actually driving this transformation. So this too is an actuator. You have many such actuators which are moving this thing around, because it's all connected to a crank. It's a single crank. So I will take that a little forward and say that this works on its own vertically. So this actuator here is where, again, I said it needs to be reset for cycling again. So you have this shape memory spring here, and you have an elastic spring which will press this fellow, and if it becomes hot, that guy will undergo the reverse transformation and will push back, and in this case it's opening a valve, and maybe autonomously it is sensing the temperature, and it is sort of opening. Whenever it's hot, it opens a valve and lets the fluid pass. Now you can think of it as a passive smart material. And a passive smart, why? Because it is sensing the temperatures on its own. You don't need a thermocouple or something. And then it actuates. So there's a thing that can sense and actuate. It's a passive smart material on its own. Now, in order to be active, it needs to also have some kind of element of proportionality. It should understand how much more. Here in this case, it's a full force given back and delivered. So if you want to give a proportional response or a calibrated response, as the other word would be, then you need to also have some kind of an judgment. And that is usually done in these kind of materials by putting some kind of an, maybe an external computer or with an algorithm in it. And that will tell you how much to go back. Some algorithm working on a computation system. And then that entire thing becomes a smart system. And it's no more a smart material. The smart material is restricted to this guy over here. And so, okay, how would one see this is that you have this austenite response this way, and the martensite response in this case is here. And here is this the load that finally that you see, and the whole area between these two is the stroke. And the stroke depends upon because you use the spring, and we have shown it this way. It's not entirely true. It depends on the elastic constant of it. So the elastic constant will, if you have a stiffer spring, it will be more difficult to get this extension, and it will be all load. So therefore, what you will see that it depends on how you sort of intersect these two with that kind of a curve which corresponds to the bias spring. All in all, with a combination like this will give rise to the actuator. And if you were to compare these actuators and summarize this, the wax actuator is the simplest. It's one end of the spectrum in which you start with a wax and which melts in a cylinder, and there is a piston which it drives. So on melting, you have a volume change, and 1/3 of which will express itself as a linear displacement. So this thing being very small, you can imagine how much of displacement is there after all, and it's going to be very, very small. And on the other hand, the kind of stress that is, because it's a very incompressible fluid, so the stress is very high or the load is high. So you have a situation where the load is extremely high and the elongation or the movement is extremely small, right? So therefore, if you want to get higher than this, what you have to do is that you have to do using some, some kind of a combination of a jig in which you take that small strain and you magnify the strain. So that is the way you get a higher strain, and then you get a lower load in that case. But the loads are high and the strain is, or the stroke is very less. On the other end of the spectrum, you have a bimetallic strip, and the well-known bimetallic strip, which is actually where you have a difference of thermal expansion, and you get a very large change of shape, but you have a very low load. So the world in between is the world of possibilities if you look from nickel titanium point of view, because nickel titanium has a high stroke of 6 to 8%, and it has got a high load also, 500 to 1000 MPa, severely high as far as applications are concerned. And even the strains, we hardly use those 6%. It's only 1% strain that you will finally use. So it's very large, and then it's good enough to replace. And as you see gradually in the market, most of the old actuators are being replaced by these. And the advantage of this is these are very compact. And if you see some of those applications, I'll show you how compact they can get to be. So the first one which I will take is this explosive separation device, which is normally there when you have these bolts and you need to separate two surfaces which are latched on together. Let's say this bolt is latching these two surfaces together. What is done is that there is a notch which has been machined onto this, and when you stretch it in the tensile mode, the notch will separate these two. The bolt will fail and the latch will, the two surfaces will separate. And this is done, the force is generated using a explosive. And usually the problem with this is the explosive can be unstable. It can also misfire, and you can have all these kind of situations. So this is it is applied by and large. This is the most popular application, but there is an alternative when you use shape memory that you take. Let's for instance say that the equiatomic nickel titanium, which was shown, the flower was made of that, which you can deform it at room temperature in the Martensitic condition, put it between the bolt, and you heat it with some heaters. Now, phase transformation will always take place. Nature assures you that it will always take place. All you need to do is take its temperature above 80 degrees, you heat it, the thing will regain its original shape and will stretch the bolt, and we can design it to fail also with that. It's very simple design, because the 6% you can magnify it here, and depending on the notch dimensions to this dimension, you have to just take the ratios of these two. And you can imagine you can magnify it to even 15-20% and much more. We can magnify it and make it fail. So even steel bolts, we can make it fail. It's a very easy design to make a non-explosive separation device. So it's just to show the difference between these two. An explosive is in milliseconds, and non-explosive will take 2-3 seconds for it to, and if you can afford to, as is the case where in space and other applications, or in safety devices where you need to actually, pass water or open a wall, this may be a very good alternative. And so that is a simple kind of actuator. The actuator which you see in Shinkansen, which is a bullet train, and a couple of which may come to this country hopefully soon. And in that case, in that train, what is done is again a very simple application where you have oil that heats up in the gearbox, and you need to cool it. And when it gets beyond a certain point, this smart actuator opens a valve, passes it to a radiator, and it cools. So that's as simple as that. But the compact thing which I pointed out earlier is that seen in the camera. You can just think of it using a rotary to linear kind of actuation. Just use a wire and you can do anything you want. You move the shutter or anything, and any other thing that you want to move. So the compactness, the kind of thing that you get in terms of making it compact. And of course, there are a whole lot of other application one can. These are all dated slides, but you can think of some safety devices. It gets hot, it opens a valve, and the steam is let out. It doesn't scald you, so it's anti-scalding devices. But one thing which I personally like is this one, which is actually this is for a shower, and for those who enjoy a very good shower, will find this very useful. Where you have a wall where your hot and cold water mixed, and this often happens when you're in an apartment block where a lot of people are, the demand on water keeps changing, and with that you have to keep resetting this knob. So those who have gone through this will sort of will agree with me that one such device which is autonomously setting the temperature will be very useful. And the most available product is a Toto project. Toto by Toto. Toto is a very famous brand. and Toto releases this called the shape memory mixer. So you see this, and so what it does in autonomous fashion, it sort of mixes. So there are many such examples, and I'll not show you more except for one more. In the case, you can also shrink it down and make micro electromechanical system, or this called the MEMS. On MEMS system, the advantage of nickel titanium is that this has got a high resistivity. So you can trigger TTL voltages, and then so you make it very thin as a film, and in addition to all other things, you can have an actuator at that scale. So you have an actuator triggered with things, and anyway you have electronics on that scale anyway. So all that put together, it's very easy to conceive of such devices, and there are a lot of successful cases already that are there being applied, and some people who are pushing in this direction of making MEMS. I will come to this example, which is the one which we have done here, and what we have made here is a heat shrinkable shape memory alloy ferrule, and this opportunity was given by ADA, or Aeronautical Development Agency, and I saw Dr. Ashok also sitting among the. I don't know whether to call it an audience or an audience. So what do you call? So all the sitting here. So I have Dr. Ashok also, and the manager will remember very well. So it's an opportunity given by ADA to us that the application is very simple, and I should start away with showing you what that application. So what we have is this light combat aircraft Tejas, and it's already back in the news in the sense that the government is pushing behind this for application and seeing that it's deployed as quickly as possible. For all those people in the Tejas project, I think my congratulations to them to have brought this aircraft so far, and possibly as it will also see some action in future, and it's already on the way to replace the MiG-21s, and so I feel they have done an excellent job. So our role came in making these kind of sleeves, and what does it do? The issue is very simple at hand. This aircraft, by and large, it is the skin of it. Most of the skin of this aircraft is actually a carbon fiber composite, and which means to say, despite being carbon, it's not a great conductor. So you have a lot of static building up, and occasionally when they discharge, they have also some kind of conductor, like a copper conductor, like a mesh, put into the composite. In spite of all that, you need to also protect any long tubing in this. In this case, is aluminum tubings, and these are conduit tubings which either carry fuel from the tank to the fuselage and onto the engine. So most of the fuel is in the wings, and there are two more tanks, I think, in the fuselage and one close to the engine. So these secondary tanks are also there, and you have these lines carrying the fuel, and then sort of the entire loop of this piping that is in the aircraft. You can't. You have to see that the current it has to be interrupted. You have to have an electrical insulator which interrupts its length, and for that they had selected PEEK, the polyethyl ethyl ketone, as the insulator. It's an elastomer also, and you have to just latch it onto this aluminum pipe. Now it looks like a simple issue. You could have also used Teflon or nylon or something like that, but equally well. But I think PEEK is by far the better material. And the difficulty was, how would you latch it on? Now, when you hold on to this PEEK, this will sort of shrink. I mean, it is elastomeric because it's an elastic material, so it will give way, and that is about 1% of it in this application. About 0.8% will actually relax. So you have to have a stroke which is more than 0.8. If you look at heat shrinkable, you have to have a stroke much more than 0.8% to do. Most materials show elastic interference only 0.5%, and if you look at normal heat shrinkable, it's far less than that you get that what you call the shrinkages, because you're trying to do with thermal expansion. So this is not thermal, this is actually a phase change. So what is done here is that the service window for this application is between -50 and +150 degrees. So this material, which we have got a 3-atom% iron in nickel titanium, where the iron goes in place of nickel in the lattice. So in this case, what is done is that the transformation temperature is something like -65. So it's sort of by about -50, it has recovered its original shape. And so that means in liquid nitrogen is where we deform it. And when we deploy it and take it to liquid nitrogen, it will come back to its original shape. And between -50 and +150, it will deliver a constant stress of about 500 MPa. or 70,000 psi, and this will help to put the insulator onto the tubing. Now, there's another feature which I think if Dr. Ashok later on, if he wants, he can also say whether I'm right or wrong. But this aircraft is made slightly flexible, and that is one of the features of this. And they get there are some dividends aerodynamically when you make the structure slightly flexible, which also means that all these pipings which are not on the neutral plane, they will be pulled apart. So the total stresses that this material sees has to be seen by this particular nickel tide. It's hold out against all that. So you need a constant stress. It is not just interference stress in terms of minor interference. It needs to be a constant stress that applies. And that is what this simple application gives. So all of them just look like bangles or something like that. And between about 55 mm to 20 mm, there are four of which are shown here. And this is the place you can see that there is a pipe and this insulator is placed. I hope there's a film which I show. This is a very dated film, maybe 98, 99. It's analog and there's a lot of color bleed. Essentially, Dr. Ashok is responsible for it, and he made it. And he got it made, the movie, and I will show it to you if it works here. But I'll go on to the next slide. This is another set. This is in the drop tanks I use. You can see it more clearly. You can see this insulator, and you can see these two rings holding on to this. Application looks very simple, but if you talk it in terms of what has been the kind of stresses that this material sees, and both rotational, you have a kind of pulling and bending and all these things that you see here, you need something to hold on to this. And like I said, there's one more thing that because being elastomer, it has to shrink and yet have strain on it. At that point, I emphasize as I go along. And this is the movie which I will try to run. And this is again, I must give there's a total credit goes to Dr. Ashok. And I let me see if it runs. And I hope and I wish, yes, it runs. And what you're seeing here is the wing of the aircraft, the delta wing of the aircraft, and they make it. And you can see this pipe, that is shown in another figure, and this insulator there, which is held together with this. And in the following figure, you will see that they're just collecting some liquid nitrogen. Now, all this has been made for the movie, right? So usually it is done in another way, and I'll explain that. These rings are expanded in liquid nitrogen. Like I said, it recovers by about -50, -65. It recovers the original shape. And the purpose of showing this is that this is some kind of a radial expander, radial pipe expander or tube expander, whatever you want like to call it. And this is being kept in liquid nitrogen, a little crude the way it is being done here. But there's a purpose to show this, that when you're actually, turning it like this, you're actually expanding it. But look at this, it's so easy to do. If you have 1 mm thick ring, which has a yield stress of about 1,000 or 1,200 MPa, more than a GPa, then it would have been very difficult for you to deform it. But you can see it's so easy to deform. And that's because only 100 MPa is the stress required to deform. 1 mm thick ring, you simply cannot deform it this way. So now what they do is they deform it to something like about 6%. And this is stored in liquid nitrogen till the time of deployment. And at that time, here he's stripping off the paint, applying some Bostic sealant to this to make it gas tight, and in a wink of an eye. Now you have to be careful to see this, because they use a tweezer or a tong, any low profile tool hardly requires. That's it, it's done. And it links, and the moment it shrinks, it's applying a stress, it's almost virtually fit and forget, to the extent that if you have to remove it, you have to virtually cut it out. And it's an intermetallic. So, you have to put in some effort there. You can see a few examples of it where they're putting all such components where they have to link up in the aircraft. They're roughly about 250 sleeves. I mean, I think if Velpari is MS Velpari, who's director planning, if he's operations, if he's there of HAL, sometimes he can tell how many are there right now. So what they do is that they put these rings together. This is just to show you for different areas. Okay, this is the first flight of the aircraft, and this is a very proud moment for the country, and it was also equally proud moment for the team which made the heat shrinkable ferrules. I think a lot of whom are watching this presentation at the moment. It's an extremely proud moment for those people. It's all the way to, it's the first flight, and it has probably been deployed at the border. So I wish them all the best in future development. Of course, our association was because of shape memory, and I need to go a little forward. Just to explain some of the advantage of fasteners, this is just to summarize. You have a large recovery strain. We have said that it's a constant recovery stress. It's a finite, and you show the plateau in that stress-induced martensite. That's the constant recovery stress. It's like a bangle. So it just puts it, and you can sort of do anything to it. You have a uniform radial pressure on account of it. It can be sort of it can sort of wrap itself around that object, and you have a low installation temperature because that's what it's much less than 150 degrees the application temperature. You have a low installation tool, hardly any profile. It's just a tweezer or something like that. Of course, you can apply to dissimilar metal joints. All this go in the way or to apply to credit it. So how do you design this? Now I'm coming to the final few slides. So I just wanted to say, how do you design this? Just for the interest of people, that you start with 6% strain. And that's all you got. And I say the most difficult part is strain accommodation with the polymer. The polymer sinks because it's an elastomer, and it has to sink by the elastomer because it has to transmit that stress. That stress or the strain is transmitted through this polymer onto this interface, and that is a holding stress. Unless it transmits, if it was very hard, it would have transmitted. It has to transmit it. So it has to. It's some material with only about 3.5 GPa. It will transmit that stress, and it will hold this polymer against the pipe. So that's what it does. So in that, it loses some strain. So that is about 0.8% strain in this kind of situation. You start with 6% and you say, I want to have some even at the end of the day. So that's some assurance that there will be some strain which is always locking, and therefore there is a constant stress always acting on it. And we say this 1.5% strain in the design. So you got 4.5% strain to play with, which is lost towards dimensional tolerance, differential thermal expansion, elastic spring back, which means to say you deform it in liquid nitrogen, and when you let go 0.5% strain, you lose that, and some installation clearance, like 50 microns, but we can do with 25 microns if the situation is bad. So it's something like 25, 50 microns. So you can do all this to calculate the dimensions of the coupling or the ferrule in this case, and just to show that how do you calculate these things. So you have got a pull-out stress, and that you know already, and from which, knowing the decay, you know what the stress that needs to be applied, and if you know the coefficient of friction and all that, so you can work it out with some kind of safety factors. You can work out the kind of stress that you need to apply, and therefore you know the width of the sleeve and the thickness of the sleeve, and you also know how much of the elastic it is actually, this peak is actually accommodating. It's a very simple LEBV type of problem, and from that we can get the sizes of this dimension of this. Effectively, it's a sleeve which is smaller than the peak insulator, is put in liquid nitrogen, expanded, put on top, it recovers its original shape, and it still has 1.5% strain on that material, so that when you apply it in a condition even up to 150 degrees, you can twist, and up to the limits what it has been designed for, it can still fold out. So that is that application there. And just to come to what we have done finally is we got an opportunity to also transfer the technology to through a tripartite TOT to Foundry and Forge division of HAL, and if MS Velpari and Praveen are there, they're solely responsible along with Dr. Ashok. They're the driving force with helping us or bringing about this transfer of technology to reality. So you'll see that what we do in this case is we start with nickel titanium pure elements. We melt it in induction melting, and this is a 3-chamber induction melting. After melting, we get something like a billet, which we do arc melting, and it's a vacuum arc melting. And then we do hot forging. Here we do hammer forging. It's very essential because it's a material which shows adiabatic shear banding, extensive amount in the original dendritic condition or the cast condition. What you need to do is hammer forging. It turns out there is a DRX window, a dynamic recrystallization window in that. So this was a work which Dr. Ashok and us, we did it in IISc, and that I think it's Professor Prasad. That was his final work also. Thereafter, he moved away from IISc, and we could do the deformation process maps for this. And you see a window in which you can actually forge, hammer forge. And I was very uncomfortable in the beginning because hammer forging, you hammer it, and my heart was always in my mouth. That's what the material is. But it turns out that is the only temperature, only condition under which you can actually deform it. In fact, if you press forge, it'll fail. In hammer, it'll survive. So that is a kind of materials that show you different character. But once you have forged the hammer and the dendrite keeps breaking down and you have equiax grain, it sort of opens out the DRX window. It's very easy to roll, and by a combination of single point machining and also grinding, we can, and of course we cut it out by EDM, and we can take out the final sleeve and do some transformation cycling, and we do some tests, and this transformation cycling is trying to impart some kind of memory to it. We do that to get the final sleeve. These are very sort of, the dimension tolerances are very good, because you can see in the calculation which I showed, everything, it adds on to that 6% strain. That's all we start out with. The size is very small, it's very constrained. And just to show you the plant which they have in Foundry and Forge division, and it is Mr. Praveen who's standing here, and this is their plant, and they have successfully made what they have informed is 42 aircraft sets beyond the 10 that was initially made. So all of them will be seeing, I mean, most of it is seeing service. And so this has been a plant that has come out of this effort, and a very successful transfer of technology from a lab. And for most of us who are in the lab, it's a matter of pride that all of us could come together to bring it from the lab to deploy it in actual application. And so we hope that more aircrafts, 83 more aircrafts, at least, well, that's what they say, are sanctioned, and many of these this plant will produce. So what is the way forward is one more thing which we believe it could come, is a hydraulic coupling. Now, there we were joining a peak insulator. Here we are taking titanium half alloy tubings, which are used for hydraulic. For you need to move the control surfaces for which you have hydraulic pressure. So if you join lengths, you conventionally do that with something which is swaged. So that fellow is a heavy guy, which you have to swage it on the top externally with quite a major tool. And this has to have some swaging, teeth on either side of the tube. It has to be swaged to lock on. So that's what is done. And this swaging which happens, and that's so what the nickel titanium shape memory alloy does is that it's very easy to deploy. You put in liquid nitrogen, open it up, and then when you apply it to the tube, it will sort of self-swage. It's a heat shrinkable, and it will swage these rings onto the tube. It can be made very strong. It's a very strong material. It will swage onto the titanium. Now the real advantage is that this fellow is only 5 grams, as against some that may be about 150 grams or 200 grams. So what it does is saves weight in an aircraft, and it's again fit and forget. It's always constantly applying. So the interference recall is very high. It applies a stress of 70,000 psi again. So I hope that this application is finally deployed. We have extruded nickel titanium. We are doing the extrusions on this bar of this one, and some tubings are under development. We are just trying to get over some problems of pilgering. If that is done, then I believe my colleagues who will be doing that after this. I hope and believe that this will come out to be an application in both the new Mark II LCA and the other aircraft that ADA is also designing and HAL is building. And with that, I will come to the last part, and I must acknowledge first all colleagues of Materials Group and all the friends and well-wishers across a lot of places like DAE, IIT, ISC, and HAL. I specifically take Velpari, who's today Director Operations, and also Shri Praveen, and from ADA, Dr. Ashok, and also Dev Kumar, with whom we had very good interaction. And special thanks in this is due to BC Maji and also VC Krishnan Nair, because they are the people who are the other parts, and I'm delivering the talk. There are other members of the team from BIC in the application that you saw in the aircraft particularly. So I thank the organizers once again at the end of it to give me this opportunity to tell something about shape memory, and I hope it enthuses some of the young people who may have tuned in to see that how we can, it's not only that alloy and the kind of phenomena that is there in shape memory. I think a complete study on phase transformation and taking it all the way to applications. I've been very lucky that I could do it, and I hope and I wish you all the best that whether you get an opportunity to do the same, and if possible, take it all the way to an application. Thank you very much.